It's my huge privilege to introduce today's users who are going to be talking about their use of DDS. And let me give you a little bit of bio background on them. Christine Judd is the Vice President of Metron, Inc.'s Unmanned Systems Division, providing resilient mission autonomy solutions for the defense, civilian, and commercial markets. With over 25 years of experience, Christine has advanced projects across the Department of Defense value chain, securing contracts with DARPA, NAVSEA, and ONR. Her experience spans analytics, autonomous systems, and applied simulation focused on autonomous solutions to solve real-world challenges, mission challenges. She currently leads Metron's autonomy software and vehicle development programs, focusing on platform development and intelligent, adaptive AUV mission planning, execution, payload management, and self-adaptive health management. Christine is going to come to the podium, and also welcoming to the podium is Matthew Judd, and he is the Autonomy Software Architect and developer of Metron, Inc.'s Unmanned Systems Division, providing same things, the same mission.
Same project.
Same project. He also has 25 years of experience and has also supported similar projects along with Christine. In the last 10 years, he has designed and implemented Metron's autonomy, navigation, command and control autonomy suite, which is the vehicle autonomy used for both commercial and Department of Defense applications. So my huge pleasure. Thank you for joining us today. Please join me
for the introduction. All right. So I'm going to give you a quick introduction as to what Metron is, what we do, to give you some context about what Matt will then say, how we use DDS and what are some of the challenges and uses that we have DDS for and how we used it. So let's see. Close that. Okay. All right. So Metron, our headquarters is located right here in the Rescue Town Center. So it was a short walk for us to come over here. We're a small employee-owned company. We've got about just under 200 people now. Been around for a long time, since 1982. About 75 million in revenue, just to give you an idea of our size. And we're mostly PhDs in mathematics and statistics and physics and chemistry, you know, as well as computer science and developers. Most of us with master's degrees. So it's that kind of company. We work for all of these logoed agencies that you see at the bottom of the slide here. So again, primarily defense. Across the whole board. So Navy is our primary customer, but we have several others, including the Air Force and the Marines. And for my division in particular, DARPA, the Defense Advanced Research Projects Agency, is our primary client. So R&D development, I'd say applied R&D development. And again, particularly our division works for a DARPA office that is very interested in having technology demonstrated at the end of their program. So they have a 2 or 3 year program. They want to see these vehicles in the water, on the ground, you know, doing what they're supposed to be doing and performing the missions that they've laid out. So Metron as a whole, we do data analytics, looking at large amounts of data and figuring out what are the anomalies in that data. We do autonomy, which is what we're talking about, decision support systems, modeling and simulation to varying degrees, all the way from, you know, large campaign level simulations all the way down to, again, what we do, which is more individual units, hydrodynamic modeling for underwater vehicles, that kind of thing. And also the sensing side. So we often say, you know, an autonomous system can't do anything if it can't sense the environment, right? What do I make decisions on if I don't know where I am? Okay. So what are we focused on? So we have this kind of theme tagline called resilient mission autonomy. What does that mean? Again, we're like, autonomy is great. It's interesting, you know, how do you do it? But at the end of the day, autonomy, just for autonomy's sake, isn't worth that much. So why do we do autonomy? Because of the missions that the mostly defense, but also some of the commercial areas ask us to do. And those missions are generally long duration. So we're not talking about a few hours here. We're talking about days, weeks, months, even years. So these systems have to be resilient, right? They have to understand the environment that they're in, and then have to understand the decisions that they can make in that environment. So that's kind of the mission autonomy side. And then they also have to understand themselves, right? What is my current health? How can I mitigate the fact if my rudder isn't turning quite as well as I thought it was? Those kinds of things. So external autonomy and introspective autonomy is what we call those two things. All right, so since I can't talk a lot about the stuff that we do for defense, we also have commercial endeavors that we're getting into. And what are we really talking about here? For our underwater vehicles, we're mostly talking about offshore energy. So when these offshore energy companies decide to put a wind farm somewhere, they have to do a whole sequence of things that are mandated by the government, starting with site surveys, and then while they're constructing it, they have to do construction surveys. Once everything is built, they have to do, infrastructure maintenance surveys. We're talking about, following a pipeline, making sure there's no cracks, making sure that there's no subsidence under it, or it's covered when it's supposed to be covered. So these kinds of things. And right now, they do these inspections from a surface vessel of some sort, and ROVs, remote controlled vehicles. So that takes a lot of people, it takes a large boat, it takes a lot of time. What they're starting to explore, and what we're involved is having these large underwater vehicles go out there and do this all autonomously. So some of the things, I kind of mentioned a few of these, but visually inspecting it, using different sensors at different times, so switching systems on and off, understanding whether I'm on track or off track. All of these things kind of go into that, as you can imagine, if you're out there for days and weeks and months, in order to bring back this data at the end of the day to the customer. So this is kind of an overview of what we do. I'm now going to turn it over to Matt, who's going to talk particularly on where DDS comes into all of this.
Okay. So now it's going to the specifics of how we do it. So a lot of the things we've just been hearing about are the things I was focusing on here. So our first use case is we actually develop the system. So what does that mean? So we have to simulate the world. So there's going to be a pretty high-powered computer in the network that's running the simulation, and that has to feed the data to our system that we would be getting from real sensors. Then we've got our actual deployed autonomy. Our target, the vehicles we run on tend to be power constrained, so we are usually running on low-powered computers, ARMs, iPhone kind of computer system. So it's really, I don't know it's as low as some of the standards I've seen. They were for very resource constrained. I don't think we're using anything like that, but we are, it's not a really big high power computer. And then we've got some tools for monitoring. I'm going to talk about this more with the post-mission analysis, but our GUI that we use for live monitoring when we're running in sim is Java. A lot of the people developing on that are Windows. So we're already talking 3 architectures, 2 languages. So having something like DDS to support that is really important. Trying to implement that, at the byte level is nightmarish for anybody as old as me who has done it before. So we don't want to do that ever again. And so what I'm listing there on the right is, so those are the 3 architectures, and I heard somebody, previously talking about the different kind of data flows. So the sensor data tends to be same size. There's not really a lot of variance, high frequency, and the guaranteed delivery is not that important. You don't want to get backed up. So if you miss one, you're just going to get the next time. Command and control messages are intermittent. They can be vary in size widely, and it's really important you not miss any of those. So those right there are 2 different use cases. And then we have a set of messages I call the monitoring messages, but there's a whole lot of data that we publish that is really for us to figure out what happened once we get the vehicle back and pull a bunch of data. So those are really important for our PMA, and they're very important in this development phase when we're live monitoring. Once it's out in the water, they are lower priority than the other things. So it's a good range of the topic requirements. All right, so which one is it? All right, so the deployment, like I say, so these are power constraints. So once we actually put it on a vehicle, these are large vehicles, but from a computer system standpoint, it's a small number of computers. So it's a closed network. We're not, a lot of the kind of capabilities we were talking about before, recognizing new machines popping up and going away, or dealing with network problems. These are not our problems. We have got one connection between two physical bottles. If the line is broken, there is no way adapting to it. And so one thing I do call out, so something that capability that we're getting from DDS, or from our vendor at least, that is really important is a logging service. So just log every DDS message published for later use. So that's really important. Our base system is a small number of processes, usually on the same computer. But one of the capabilities we're trying to support is, different use cases. We'll have a payload or an extension, possibly in a different bottle, where we just define the interface of the data we want to get back and forth, and we don't have to know how they're implementing it or why. So DDS is obviously very good for that. And again, so on the right there, I'm talking about the requirements on this side. So now there's no Java, there's only the AMD. I meant ARM there, but it's only the low powered message there. And like I say, the PMA messages at that point are really low priority. All right, then the analysis. So the way this tends to run is the vehicle is out there for some length of time. Like Christine was saying, some of these missions can be really long. We're going to be logging all the data that we can. Sometimes that data gets really large. And the first thing we do when we pull the vehicle out is pull, gigabytes of data off of it and try to figure out what happened. And so this is where a lot of the capabilities from DDS and using this structured data has been really important. And so we're going to show a little video after this of a tool, the tool we use for post-mission analysis. But all the data that we show in that video is logged DDS messages. And in the past, when we were developing a new machine, a new vehicle, as well as the autonomy, we could use that data to go and identify a wide range of failures, including actuators breaking, getting caught in a fishing line, and the vehicle changing direction in a way that we didn't think was possible. A lot of other things. And the important thing that we got out of that was we didn't know before the mission started what data was going to be important to figuring out the failure point. So being able to capture all of the data that flows across these pieces and being able to access it quickly and visualize it really speeds up the development and analysis problem. Yep.
Are you able to adjust the velocity?
So we're using RTI's native logging system. There's a lot of configuration in that. I haven't had to explore it yet. We haven't used this for a multi-week mission yet. I'm sure it can. I'm sure it can. So that will get really tricky once we start trying to do that. Like I say, we don't know which data is going to be important. So we don't want to tune it down too much. I'd rather throw more disk space if possible. But yeah, so that even our long missions, like I say, these vehicles are power constrained. So if it's a really long mission like that, it's probably spending a lot of time with everything off. So there's not a lot of messages flowing. All right, so what else did I want to say on this? I think that's mostly what I wanted to say. So I didn't have any pattern to follow of what you're looking for in a use case. We could get into details if somebody cares about the specifics of the message, but the point is it's exactly what previous speakers are saying DDS is useful for. We can identify this structured data in IDLs. We share it across teammates. Several of these processes on these vehicles are implemented by other performers on these contracts. So as long as we agree on the structured data, it doesn't really matter how they're implemented, and that has worked really well. Any other? Let me see, what was the last slide on here? Oh, that's the video, which isn't there, so we could. So I can start the video and talk to it. No, it's not. But what it might be publishing, and so the system we were working on with that, it might be publishing the actual length. So that was a linear actuator. So some of the data it was publishing was like the actual length of the actuator, and we know for a given length what that should interpret as the angle of the rudder. And when all of a sudden, it went to a certain length and the rudder stopped moving with it, we could interpret that as
Or temperature starts running away. I actually worked with that LDUV program in prototype a few years ago, and the way you handle that in DDS has a deadline quality service where a publisher can say, I'm going to send you a message every 5 minutes or something like that. Fails to make that, they'll both be notified. So that's probably fine.
well. So we're probably talking about two different things. What I'm saying about how we use the data to analyze, it was actually publishing data that was not in the command and control critical path, but I just had it publishing state so that in this PMA phase, I could load that data and see it, right? So I'll have to talk to you later, because with the LDUV INP is when we started doing all this.
Yeah.
So we actually were working on the ONR's initial program that turned into LD. So
And I guess one thing I didn't say that is actually very important here is when these vehicles leave the pier, they're gone, right? They're no communication, no anything until they, hopefully come back, right? So, so that's why this logging is really, really important.
Layton is marketing. How much time and money you saved by using DDS rather than?
So that's an interesting question, because I have been doing this kind of thing for a really long time. I started using Corba 1.0 when I was in college, so 30 years ago. So before we used DDS, we were using active MQ and string or proto kind of stuff. What I would say DDS is really giving us is we are starting to work on systems that might potentially transition for the Navy. And the fact that DDS is an accepted technology on programs of record is not true for the kind of free things we were using before. So pub subsystems and structured data save so much time. It's like most of what kind of things we do, we couldn't even bid if we were actually going to go and try to write byte, things that were to and from in byte. But the DDS, I mean, the implementation works. So we swapped between vendors at one point pretty smoothly. So from a DDS standard viewpoint, that's probably good. So all right. So this was just a video that we made to show off our GUI to our customer. So the point is not really the GUI, but the point is all the timelines over there on the right. The red data is basically vehicle state data. So things like depth, speed, heading, coming at a pretty high rate. The little blue dots in those same timelines are the values we're commanding. So one of the things we can see from this right away is the vehicle actually following what we command. So that's the kind of thing we'd want to be able to pull out of it. So there's a whole bunch of stuff in here about. So there is a whole lot of data, timeline-based data, more than we'd want to look in any particular view. So some of the things we're calling out here is, if it turns out what we really care about is roll, then we might want to add a timeline about roll. But all that data is captured in the DDS messages. So here we're looking at commands. We're drawing a little map. So there's in that data is a lat long depth, so we can overlay it on the map and see the path.
Ignore the fact that it looks like it's on land. It's just that the bathymetry data is great. This is Narragansett Bay in Rhode Island.
So
very shallow. So
we used to test off of San Diego, and we keep being promised we're eventually going to demo in Hawaii, but those always turn into New York or Rhode Island by the time we get to that date. I know. I believed it the first couple of times. So so here on the right, you can see as we're changing target headings in blue, you can see the vehicle kind of catching up. I think that's heading. We're tracking the RPM versus speed sometimes. You can see the depth. The point of this is mostly we are generating a whole lot of data during a mission. We don't know what we care about. until and literally all we know when the vehicle comes back is it came back, which is, a successful day, but we don't know if it just, go went around randomly and came back up or actually did what we wanted until we start looking at this. Like I said, our target vehicles are really long duration, and my nightmare forever has been it happily loiters and needed death until the batteries run out a week later. So I'm always happy when it comes back. Anyway, so the point of this was really just to call out, we are capable of using only the data that we capture off the DDS to do the vast majority of our analysis. And when something fails, usually, and we're still working on getting some of our autonomy specific structure data in here, which also flows over DDS. So sometimes we have to go down into logs to figure out why the vehicle made the wrong decision. We're trying to get more of that information into this. But anyway, so that was the point of it. I think that is all we
That is